So let's just start off with the idea of a metric space. Metric spaces. And so basically a set, we have a set, so X is a set, and D is a mapping from X cross X into R. So it takes two members of D and spits out a real number. Do you guys know what metric spaces or not?
Yes.
Yeah. Okay. We'll review it anyways, just to keep things fresh in your mind. And the function D has the following properties, that D of xy is always greater than or equal to 0. Of course, x, y, z are members of X. And then D of xy is equal to 0 if and only if x equals y. 2. D of xy equals D of yx. 3, we have triangle inequality. This is for all x, y, z. D of xz is less than or equal to D of xy plus D of yz. So there are a lot of important, a lot of things are metric spaces that we care about. So for example, we can take the real numbers and let's say the absolute value, let's just say the absolute value. So we have that D of xy is absolute value of x minus y. Okay. You can check that all these conditions are satisfied. We can also look at, say, r to the n with, let's say also d of, let's say, x1 to xn and y1 to yn is the square root of x1 minus y1 squared up to xn minus yn squared, for example. There are other interesting things you can put on here as well. This isn't the only one, but this is just a simple example. 0, 1, you can also, there are going to be some differences what happens if we look at a closed interval versus an open interval. These are both metric spaces, for example, with that metric. Some different things will happen, like for example, continuous functions will achieve a maximum and a minimum here, but not in here necessarily. So we'll talk a little bit about compactness as well. 4, this is a good one that's a little more abstract, the discrete metric. And this is a metric you can put on any set. So we let S be any set, or let's say let
not empty.
Okay, let's say let X not empty be any, say, non-empty set. And we define D of xy as follows, as 0 for x equal y and 1 for x not equal to y. So this is kind of the first, let's say, sort of abstract example. And there are many, many, many other examples. We'll mention some others that we care about. What's an open set? So definition is that S subset of X is open. We care a lot about open sets and closed sets. If, let's say for all X in S, and there will exist delta greater than 0 such that the distance between x and y less than delta implies that y is in S. So in other words, you have some funny set here, and wherever your point is, there exists some small little number delta where you can draw a ball around and everything around is going to be within set S. So for example, 0, 1, this is not open. So 0, 1 is, this one here, this is open. So we get this problem at the boundary points, right? Because anywhere inside here you can draw a small ball, and the same here, but we get this point right here. Anytime you draw a ball, you go outside. Okay. And this is a closed set, and there are, some equivalent definitions. We can just say a set is closed if it's a complement of an open set. So we want to talk about continuous functions. So let say f from x comma d1 to y comma d2. So these are metric spaces. And then we say then f of x, and let's say f is continuous if for all, let's say x in x, and for all epsilon greater than 0, there exists a delta greater than 0, where d1 of x, y less than delta implies that d2 of f of x, f of y is less than epsilon. So if you want your function to vary by no more than epsilon, there's a way to guarantee that. There's some delta where if you're delta close, this is guaranteed. This can sometimes be a hard definition if you haven't seen anything like that before, but I guess this is familiar, so we can go slower. Okay. And note that f inverse of open sets are open. So if you take an open set, you apply the inverse function to it, you get back an open set, and that's an absolutely key and critical property. Exercise. If you haven't done it already or haven't seen a proof. However, you are not guaranteed that if you apply an open set, you apply f to an open set, that you get an open set back. Do you guys know any examples?
Actually, we mean the first open set in the set of the one metric space,
yeah,
but the answer in the initial.
Yeah, because so f inverse is going to map y to d. So this is open in y, and then this is open in x. So if it's not clear, we have two completely different spaces, right? So maybe y is some sort of discrete metric type space, weird thing, and maybe x is r to the 7 or whatever. They could just both be r. Either way, f inverse has a domain of y, so or domain of image of f rather, and
in general case, the continuity depends essentially on metrics in both spaces.
Yes, absolutely, yeah. So the metric completely changes everything. So whatever. So if you take the same sets, it's not a property of the sets themselves. Like for example, you could even take the reals. You put the discrete metric on the reals, and everything completely changes what's an open set and what isn't, and so it's property both of the set and the metric. But of course, the metric is determining what are the distances in the open sets and everything. Do any undergraduates know examples of, say, like any metric spaces and a continuous function between the metric spaces where an open set gets mapped to a set that's not open? This is not a question for professors. This is a question for undergraduates.
I may assume if we take the real numbers and the from 1 to 0, we can say, well, I can have the open set from 1 to 2p and have function like sinus of x.
So hold on, let's make sure I got this. So your metric space, your first one, x is
reals,
okay, and then and I guess we're just assuming the standard Euclidean metric.
Yes.
And y is reals also, or something else?
No, it is not the interval, the close one, from 1 to 0.
1 to 0 or 0 to 1?
From 0 to 1.
0 to 1, okay. And then your function?
Sinus x.
So sine of x. So let's say f of x is sine of x. So what's the open set you start with?
It's an example from 0 to 2 pi.
Okay, so let's say we have 0 to pi open. Okay, so sine of x is going to give you, because this is going to go from 0 to 1 and down. So f of 0 pi is going to give you, right, this is going to be 0, 1, right, yeah, like that. So that's not open.
No. 0 should not be included.
Exactly.
1 should not be excluded.
Well, it's there. So it's square. And
Yes.
So we're not including 0 and we're including 1. So this is left open, right closed, so it's not an open set, so that works as an example.
Maybe not from 0 to p, but 2 pi. It will have all its maximum and minima.
We just want something that maps an open set to a not open set, and that in your example worked.
From 0 to 2 pi, not?
If you change pi to 1,
Pi.
you will not have a counterexample. So if you change pi into pi or 2,
Yeah, so this is because what's happening here is, right, you're going like this, right, here's pi over 2, right, and so you're not hitting 0 because you're excluding there, but you hit 1. So you get mapped to a half open interval 0, 1, so it works for.
Why can't I have from 0 to 2 pi?
Well, yeah, because the problem with that.
you will have the same good situation.
Yeah, well, that's because we do hit 0, because the problem then is f of 0 to 2 pi. Right, this is, oh yeah, you get a closed set, so yeah, that works then too. So that's minus 1 to 1, okay. So it also works. It gives you, rather than a half open, half closed, you get a closed.
Yes.
Sorry. I'm going to be really slow today, so I apologize.
Sorry, I'm bad communicator.
Yeah. Also. So yeah, anyways, we see that some examples like that. Okay, everyone good? So let's just mention a few more things before we go on. So compactness. So we say that X is compact if every cover contains a finite subcover. So this means if there is some way we have of writing down a whole bunch of open sets and their union contains X, or let's say maybe S subset of X, just to be clear that the open sets are coming from X. Yet no matter what way you write S as the union of a bunch of open sets, there's some finite collection that also covers it, then your set is compact. So theorem, Heine-Borel. So if X is, let's say, R, comma, let's say the Euclidean metric, then S subset of X is compact if and only if S is closed and bounded. Useful theorem. What if we have something like the discrete metric? Let's say we have X and we have D, and this is the discrete metric. When will this entire space X be compact? Does anybody know?
When it's finite.
Exactly. So, do you guys know that?
I'm not.
Okay, good. If you don't know, take it as an exercise. Okay, good. I'm glad we can move through all this stuff quickly. So what else? We have discrete metric. We have also, we note that you can prove or take this as an exercise is that arbitrary unions of open sets are open in any metric space, and finitely many intersections of open sets are open. So like, for example, if you were to do some countable intersection k equals 1 to infinity of these open sets minus 1 over k to 1 over k, you just get the singleton 0, which is a closed set, which is not open. Okay. So you can't extend this necessarily past finitely many sets. Also, I forgot to note that continuous functions achieve mins and maxes on compact sets. It's a useful thing. Okay, so let's continue on. Straight out a discrete metric. And do you guys know about F sigmas and G deltas?
Repeat this.
Does the term F sigma or G delta mean anything? No worries. So we say that S is an F sigma if, just a second, it's the if it is the countable union of closed sets, and we say that G delta if
countable unit of closed sets. So the is it interval belongs to the set?
Oh yeah, I'll get to examples in a minute.
Of a finite unit of open set.
I'll get to examples like that in a second. But yeah, there can be more simple sets. So just 1 minute. G delta if it is a countable intersection of open sets. Yeah, I mean, so some of these are completely trivial. Like, for example, the singleton pi is also, the union from n equals 1 to infinity of the singleton pi, right? So it's both closed and an F sigma. So there are a lot of things that can be, so, countable union, I think you're asking about open intervals. So we could look at, for example, the union from n equals 1 to infinity of something like minus 1 plus 1 over k to 1 minus 1 over k. And this is closed. Let's make it closed. So this is a countable union of closed sets. Well, this just happens to be the open set minus 1 to 1. So basically what's going to happen, but you can have more interesting things. So for example, if you want to look at a countable union, here's another F sigma, look at the rationals, which is the union over Q, and is kind of a dumb thing, but it's how it works, is the countable union over Q and Q of the singleton Q. So this is neither an open or a closed set, it's something new, it's an F sigma. And then the irrationals, so this is F sigma, and then R minus Q is a G delta, sigma G delta. So you can have open and closed sets that are F sigmas or G deltas, but then you can also run into new sets. And then you can imagine repeating this procedure further and further and further. And you can potentially get new sets, and that's kind of a question. When you're guaranteed to get new sets, because depending on which Polish space, so I haven't defined that yet, but which Polish space you're in, it may stabilize at some point or give you new sets at every step. So I don't like this notation, because from my perspective, I want to even take this through countable ordinals, and I don't want to just write sigma delta, whatever, it gets confusing. So part of what we're going to describe with the Borel hierarchy is what I think is a much better way of describing sets produced in this manner. And further, we're going to have a full characterization of all Borel sets. I'll define what a Borel set is in a little bit. Okay, so let me think. Do I actually really need to define topological? I'll define it just so you guys can see it, but I think we can kind of get away without it. But let's just define it. So in a metric space, as an example, of something called a topological space. So we consider a pair x comma tau is where tau is a member of, I always learned it as the power set of x. So depending how you want to write it, this is the set of all subsets of x, and that's a set of all subsets of that. So in other words, this is the collection of all collections of subsets. Basically, tau is some collection of subsets of x. We're going to call these open.
Like 2 power x?
Yeah, that's also this notation that's used as well. So we look at some collection of these, and we say that is a topological space topological space if 1, we have the empty set and X are members of tau. 2, we have arbitrary union of members of tau are in tau. And 3, we have finite intersection of members of tau are in tau. So exercise, all metric spaces are topological spaces. And you would take the, say, open sets and make the open sets into your collection tau, and then it's a topological space, and it's not overly difficult. So this is a very important concept that shows up all over the place in math. I don't want to say too much because we're just really quickly going over some basics. Do you guys know what a sigma algebra is?
It is worth to explain in which sense metric spaces are topological spaces. So the topology which generates by metric.
Yeah. So you would take the open sets to be those that are described by the metric. So I had this definition of open set from before, and just take tau to be the collection of open sets and check that. You can take arbitrary unions of open sets in the sense of open in the sense of metric space, finite intersections. So I'll just write it anyways, but I guess you've seen it already. So we say that definition, let's say X is a sigma algebra, so X a set, and sigma is a member of the power set of X is a sigma algebra. If, and then we have a few conditions. 1, we have X in sigma. 2, we have sigma is closed under complements. And 3, sigma is closed under countable unions. So there's some simple observations, like I just wrote that X is in sigma, but the complement of X, which is the empty set, will of course also be in sigma, and there's a bunch of stuff like that. So I guess you guys have already seen this. So I want to define the Borel sigma algebra. And the Borel sets will be very, very, very important going on, so I just want to make sure that everybody's following where we're at here. So we say that the Borel sigma algebra, and we're going to call this like fancy B of X, is the sigma algebra generated by open sets. Okay. So we wanted to have all the open sets.
Actually, if nobody knows, which means minimal sigma algebra generated by some subsets.
So you would intersect over all possible sigma algebras that contain the open sets, is what we mean by minimal. So is that, we want good that you brought that up. I want to make sure to you guys, is that totally clear what we mean by that?
Yeah.
Is it clear to you? If to everybody? If not, please tell me if it's not. Okay, and so we want to characterize members of B of X. These are very important sets. I'll get into the motivations as to how we do it and why we do it. And so, we can start with open sets and closed sets. That's a standard thing, but then we have our F sigmas and G deltas that we looked at before, but then there's an idea we can keep continuing that process. And I want to mention a theorem as well, is that, so let me give a definition for definition. is that S is analytic if it is the continuous image of a Borel set and then co-analytic if it is the complement of an analytic set. So I think that's an unsurprising way to define it. And it may not be, who was the one, was it Lebesgue that originally just assumed that an analytic set must be Borel? Does anyone remember? It was Lebesgue.
Lebesgue, yes. I mean, not only Lebesgue, but people just seem to, assume for granted that continuous images of Borel sets are Borel until someone found a counterexample.
Yeah. Analysis is weird. There's so many.
The notion of analytic set is rather complicated. Maybe you know a battle between Kolmogorov and Suslin, who was the first to study this.
I see. And there's also a lot of other characterizations as well. I just wrote one of them, but I don't know all of the history, so if anyone's interested, Professor Torben can probably say more than me on this battle. Okay.
The Suslin was a pupil, student of Kolmogorov. And after that, a lot of misunderstanding and
there was drama, there was beef, That's we would, I don't know that we say in, I guess maybe 2025 or I don't know.
Is that more or less an example of analytic set which is not Borel? Of course, it is impossible.
Where this comes one way, where this is interesting to us, is that theorem is that S is Borel if and only if S is analytic and co-analytic. So this is a nice fact. And I definitely have come across in one of them. This is nice. So this is going to actually be related to a lot of the ideas I'm going to be going to be writing down with it in a little bit. But there was a very interesting set that came up in one of my papers that's dealing with special alpha limit sets. Maybe we can talk about it in the next talk. But where we came up with special alpha limit sets, always analytic, but we cooked up a very crazy example where it wasn't co-analytic, and this solved the problem of Mishurevich, Snoheim, Koleda, if these sets are always Borel or not. But this says for the entire Borel hierarchy, you can have something much lower, and an open set's going to be with both analytic and co-analytic. Okay, so I assume you guys have not seen this theorem. I'm not going to prove it. We don't have time. I'm not going to worry about it, but just so you know. Let me actually give an example of something. This is going to be one that's co-analytic but not analytic, but this will be one due to Dan Molden. This is kind of a fun one. So this is due to Dan Molden in 1979. And he came up with this interesting example. We let x be c of 0, 1, so continuous functions on 0, 1. And we let S be the set of all f and x, such that f is nowhere differentiable. So did you guys see any of these like wacky functions are continuous, nowhere differentiable, things like this Weierstrass function and all this crazy stuff?
Yes.
Okay, great. I love this type of stuff. There's a book. Have you heard of this book, Counterexamples in Analysis? Undergrads, have you guys heard of this?
I heard, but I didn't check it.
It's a fun little thing to read. You know, there's you can read it in little. You know, if you want to sit down for a few minutes, read one counterexample, then do it another. It's you know, it's nice in math. You can have whole books just on counterexamples. There's another one in topology. I think there might have been one in algebra. I don't remember. I know there's one in analysis and topology, but I think there's some others in other areas that were published. But anyways, okay, this set right here. So this set is.
It's like
It's 79 or 19?
1990 or
79. 79, yeah.
Okay. S is continuous because you defined before.
Yes, yeah. S is subsets of X. So then theorem.
First better category, yes.
S is co-analytic, but not analytic. So that's a fun example just outside of the reals. We're looking at this.
Maybe I misunderstand. I was sure before that the notion of analytic set essentially wider than the notion of Borel set.
Well, there's a bunch of equivalent definitions.
Yeah. I mean, analytic set in the sense of Suslin. So there's absolutely different definition of analytic set. Essentially wider than the set of Borel set. That is why Kolmogorov, being a teacher of Suslin, and who invented the notion of analytic set, which is essentially wider than the Borel set.
Well, it is wider than Borel sets. That's what I'm saying. So a set's Borel if and only if it's analytic and co-analytic. So it's much bigger.
The definition of analyticity in Suslin, definition different essentially from.
There are many. I don't remember how many equivalent definitions are. I mean, there's a whole.
Suslin sets and the same with analytic sets. So with generalization of just the Borel set. But in your definition, actually Borel set, if and only if
analytic and well, analytic and co-analytic. So you need to be both.
Yes. But
and Molden has an example of the
definition of an analytic set. So there are different approaches to define the same notion. So just to avoid misunderstanding.
Yeah, that's what I said. There's many equivalent definitions.
Yes.
I don't have time to write down, and I didn't prepare all of them. There's some that I knew and some that I don't know.
Because Borel set, the generalization of Lebesgue set, and analytic set even wider. In Suslin set than Lebesgue.
Well, there's something also called the projective hierarchy that goes much further than just analytic sets. We are not going to be talking about this today, but we're just going to talk about the Borel hierarchy. Since the focus is on the Borel hierarchy, I don't want to go in this direction, but for those who are interested not only in extensions of Borel sets, but far beyond, you can look up this as a C, although it looks like an E. You can look up the projective hierarchy, and there are many things, and you can go even further than that. But this won't apply to anything in particular that we're going to be talking about. So yeah, you're right, absolutely. We can go much further than Borel sets, but it's going to be beyond the scope of these lectures. And much further than just analytic sets. You can go way further. That's just kind of analytic and co-analytic sets are the beginning of the projective hierarchy, and they go way further. So I want to get to the Borel hierarchy, which will be below all of this. And as well, if we care about extending ideas, there's also something called the wage hierarchy, which is a very fine, much finer way of looking at the Borel hierarchy. It gets really complicated. It's not important for what we're going to be talking about. You can also have other stratifications of the Borel hierarchy further than what we're going to do. I'm just going to be presenting just the basic Borel hierarchy. And what we start with is we'll call these sigma 1, these are open sets. Oh, and I got to also say that we're in a Polish space is a Polish space. This is where all this stuff is going to live. And this is a complete separable, vectorizable space. So complete, everyone knows what completeness is. Separable, there's a countable dense subset, that's important, that's useful. Metriizable, there's a metric on it, so. There are a whole bunch of examples of these, but like for example, 0, 1 up to b minus 1 to the n can be made into a Polish space. You put the discrete metric and then the product topology on it. The reals, you can look to 2 to the n cross n. So this is like grids of zeros and ones in the first quadrant, and there's a whole bunch of others. And so we start with the open sets, and we're going to let pi 0, 1 be the closed sets. And so the procedure we're going to do is we know that we can take the unions and intersections of arbitrary unions of open sets and finite intersections and get open sets back. So why don't we take instead, we're going to go to, let's call this pi 0, 2, and we're going to go to sigma 0, 2. So we do the opposite. So rather than take unions, you take countable intersections of open sets. So this will be countable intersections. And then here you go countable unions. And this is going to be your F sigma sets, and these are going to be your G delta sets. And I want to explain a little with the notation because the sigma referring to union and the product P referring to intersection. So basically that means that this class, when you have a pi, it's going to be closed under intersections. So you take unions to go the other way, right, to get something new. And in the middle, we're going to call this clopen sets delta 0, 1, and we're going to call this delta 0, 2. I'll write out, I'm just writing the picture now before I write down the formal definition. And then we can go again here, and we have unions preserve this, so we take countable intersections, so countable intersections, and we get pi 0, 3 sets. And here we take countable unions, and we get sigma 0, 3, and then we keep going and going and going, and we do this over countable ordinals with some transient induction fanciness and all that. And if you don't care about countable ordinals, just ignore this. For me, it never comes up, only for some, for my applications, you're never going to be using anything with countable ordinals, so that's there, but it won't do anything for us. And then we end up getting your Borel sigma algebra, which we call delta 1, 1. And then, let's just continue here, delta 1, 1, and then we're going to have here sigma 1, 1. So that's what this 0 is meaning with Borel hierarchy, and here we get the analytic sets, A-N-A-L-Y-T-X-T. And then we have pi 1, 1, we call co-analytic. So we already defined analytic sets, and you can absolutely continue on further and further and further, and this is the so-called projective hierarchy. So let's actually define what all these mean. So like I said, basically we start with open and closed sets, and then we say for any countable ordinal, sigma less than omega 1, we're going to have sigma 0 alpha is the set of all countable unions, A equal union of AN, where AN is going to be in pi 0 alpha n, where alpha n is less than alpha. And then you define pi 0 alpha similarly. Like I said, this complication here with countable ordinals can be ignored. If you just want to think about the ones we're going to care about, just think of taking, in this case, intersections of open sets to go here, and then countable unions to go over there, and so on and so on. But I just wanted to make sure that I mentioned that, and to see how we are on time. Okay, we still have some time. And I wanted to also write down a reference that will be useful. This is Kekris. And I think this is, what is it, classical descriptive set theory, I believe is the name. If it's wrong, it'll, if you Google Kekris and descriptive set theory, it'll come up anyways. Descriptive set theory. And this is a graduate text in mathematics. Maybe we have it at the ICMU. I wouldn't be surprised. I don't know. If we have a bunch of graduate text in mathematics. Anyways, it's something you can get a hold of. And this is one of the introductions. I mean, it talks about many, many, many more things, not just Borel hierarchy and related stuff. There's a whole bunch of other things that descriptive set theorists care about. And we also note that, so theorem, if X is uncountable, then we get new sets at every step. Right? Because it's possible that maybe somewhere here you get stuck and nothing interesting happens. So I just have to remark that for any uncountable Polish space, you're guaranteed that, okay, going from sigma 0, 86 to pi 0, 87, well, there's going to be some new sets that pop up by doing that. But that's not guaranteed a priori. You know, if you had like some countable or finite Polish space, there can be nothing sometimes after some point that's new. So for our purposes, we're only going to care about uncountable Polish spaces and generally anything too crazy. So we care about things like normal numbers in particular. We really care about normal numbers. But part of the purpose of this series of talks is that there are a lot of techniques that we're using here to analyze sets of normal numbers that I believe can be brought over to other areas of math. Because what's going to end up happening is that when we're dealing with some sort of descriptive set theoretic problem in some particular area of math, well, it doesn't really end up being a descriptive set theory problem. There is some kind of bridge between descriptive set theory and whatever area you're studying, and it more becomes a problem in whatever area that you're studying. And I'll go over some sketches of some proofs maybe tomorrow to show you what I'm talking about with that. So there's going to be something called wage reduction that lets you kind of transfer the problem over. And I want to also mention a notion that I think is very, very important, and if I can just even make this notion clear, I think that's already a success. So I'll just give a little bit of a story. Like a lot of my earlier work with Cantor series, when I was looking at these through normal numbers, you know, this idea that we talked about when are these notions of normality equivalent, I was always trying to find, like, is there some additional condition we can tack on to get from, say, Q normality to Q distribution normality or something along these lines, and I kept failing at this. And I was really looking for some sort of precise definition for these to be independent, let's put that in air quotes. And what some people have done is they look at, okay, you have two full measure sets, and we want to somehow argue that these sets are, let's say, air quotes, independent. Well, we can compute their Hausdorff dimension of the different sets. And this has been done. So like for example, what's the Hausdorff dimension of the set of numbers that are normal in base 2 but not normal in base 3? It's 1. Therefore, these notions are independent. For me, that's not fully satisfying. I would rather have something, in my opinion, a little better. It's going to be something different, and I'm going to define it in a little bit. But I'm going to give a notion that we're going to hopefully be able to see tomorrow. Tells you basically in some sense that you can't ever write down a theorem that says, for example, if you're normal in base 2 and additional condition, then you're normal in base 3, unless this additional condition is at least as complicated as being, say, normal in base 3. And like I said, I'm being a little bit imprecise on that. Tomorrow, hopefully we can get into some more detail, but I'm going to write down in a little bit the Borel difference hierarchy, what that is. I do need to first say what it means to be complete at one of these levels, and then I can define that. So you can have a set, like as Professor Torben mentioned, you can maybe have something that's open show up somewhere here, but you actually really see it back here first. And we want some sort of notion of a lower bound. We want to kind of say what's morally the right level that some set should be classified at. So let's say that there's a set that you see at the third level, and you found some way to write it in terms of alternating intersections and unions. And let me remark that one of the reasons we care about intersections and unions is that these correspond to for all and exist quantifiers, right? So if you look at the definition of intersecting and union, that, these are just quantifiers like that. So if you say that, if you define a set and it ends up being, say, at the pi 0,3 level, that's really a statement or a theorem about it. If you have another characterization with some number of quantifiers, it's kind of telling you where you are in the Borel hierarchy. So we sometimes want to know, when can you not appear earlier? And this is going to be the notion of being hard at a certain level, and completeness is going to be that you're found at that level and you're not found earlier. But I want to write precisely something equivalent to that. We say that S is, let's say, sigma 0 alpha hard if S complement is not pi 0 alpha. And then we say that S is, and you can chase through the definitions and you can see that that means also that implies that you're not going to find it earlier. And S is sigma 0 alpha complete if S is in sigma 0 alpha and S is sigma 0 alpha hard. So you have two conditions. You can kind of think of this like also analogous to Hausdorff dimension. First, saying that it's sigma 0 alpha is kind of like finding an upper bound. Usually this is the easiest part of it, not always, but usually. Most of the time, you can just resolve this step just by writing out the definition and counting the quantifiers. There's going to be a special technique we need to do to go here. And so here we need to show that it's not going to be a pi 0 alpha set. Or, as well, we don't find it earlier. There's going to be a technique called wage reduction that lets us do this, and this ends up usually being the harder part of the step. Okay, usually there's more you need to do, and that's kind of where the difficulty comes. However, this is not always the case, because sometimes there are sets that, by their definition, you can't even tell if they're Borel sets. So sometimes you need an extra theorem, and then on that theorem, then you can, or characterization rather, you can then count the quantifiers and get the upper bounds. So there is an example that I'll give maybe today if we have enough time. And you can do the same thing for defining, pi 0 alpha. Right, it would just be the same thing, that we would have pi 0 alpha here and pi 0 alpha. Same here, pi 0 alpha. And then this would be sigma 0 alpha. Okay, and lastly, I want to write down the difference hierarchy. And so we say that S is in D2 of sigma 0 alpha if there exist A and B in sigma 0 alpha, where S is equal to A minus B. So it's the difference of two sigma 0 alpha sets. And so this is going to be the notion that from my perspective is the most important one. Some others may be more interested in this. For me, difference hierarchy is more important. We say S is D2 sigma 0 alpha hard if S is not, see if S complement is not D2 sigma 0 alpha. And then we can, of course, do the exact same thing, replace this with pi 0 alpha, and replace this one with pi 0 alpha. And then lastly, S is D2 of sigma 0 alpha complete if S is in D2 sigma 0 alpha and S is D2 of sigma 0 alpha hard. So let me give an exercise to, I think this is a very good idea for everybody to do. It's not difficult, but I think is really important for everybody to do this before tomorrow, just to make sure that you have this exercise. The set of numbers, normal in base B is pi 0, 3. So not pi 0, 3 complete, it is. But just this basic thing here where you're going to need to write out the definition. So it's just going to be a matter of you write out the definition, definition of a limit, right? You know, for all epsilon greater than 0, there exists n, blah, 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 blah. Check all the quantifiers and make sure that everything matches up. So I think that's very important to have an intuitive understanding of what's going on. We can talk about how to get the lower bound in the next class.
May I have a small question? It's more familiar for most of Ukrainian students and professors to use F, sigma, delta, G, delta, sigma, and so on, which is the same of your classes.
In the lower classes, yes, but you're going to get kind of stopped if you go out too far like that. And it's not going to help you when you go to countable ordinals. It's the same in the US as well, that people are more used to F, sigma, delta, whatever, but you can, rather than counting sigmas and deltas, you know, you can just put like a number below, and it's could be said to be a better notation. But you're correct, this is, so yeah, is this pi, let's see, what's that going to be? So G, is it delta sigma or sigma delta? I always forget which order that goes in, but yeah, it's showing that the set of normal numbers, it's like a G delta sigma or sigma delta, whatever the notation is.
What about the class? I mean, naive question. Sometimes Borel sets are defined as any sets which can be obtained from the open sets by using at most countable union, at most countable operation, union and intersection. But it is not true. What about infinite G, delta sigma, and delta sigma, delta sigma, delta sigma, and so on?
Yeah, you're missing a lot of stuff if you only use finitely many countable.
Yes.
Yeah. That's why I'm brushing it off, but I mentioned a few times that you need to do this over countable ordinals to exhaust everything.
Explain more or less simple set, with Borel set, but set doesn't belong to any finite F sigma, delta, delta sigma, or G.
I don't remember off the top of my head, but I can tell you tomorrow. I don't remember off the top of my head. I never use sets like that, but I can
exist.
Yeah, they exist. Yeah. They exist, but I don't recall. They come up in very different places than I would ever look, so I don't remember. But do you have an example in your head?
No.
Let me get back to you on that tomorrow then, because that's a very good question, and it's one I should have an answer to, but I don't. So I'll get back to you on that tomorrow. I want to remark as well that there are, you know, what about even just further with the finite ones? Like I would always give this question. So examples that are naturally occurring tend to be up to the 3rd level and very rarely the 4th level, say complete at the 4th level. So it turns out the set of numbers that's normal in at least one base is a sigma 0,4 complete set. But I don't know any, let's say, non-artificial examples on the 4th level. But I asked this, I was at University of Michigan a few years ago, and I was speaking the logic seminar, and I always ask this question when I speak in a logic seminar, like, does anybody know any natural examples of things further out? And I think is it Trainer Harrison or Harrison Trainer? I always forget the order. He was in the audience. I think he was a postdoc there at the time. And he's like, I think I have an example. And he sent me some paper. It was some complicated thing. I have no understanding what was going on. It was some complicated thing involving some manifolds doing this, and I don't know, but he had an upper bound at the 20th level. I have no idea what was going on. I can find the paper if anyone's interested, and maybe someone can make some sense of it. But apparently there are some corners, so he doesn't know what the sort of sharp lower bound is, but there's at least an upper bound for his example on like the 20th or 21st level. Most of the time, what you're going to actually encounter is going to be complete no higher than the 3rd level, or maybe it's something that's not even Borel. Like you could have this example of Dan Molden about this set of nowhere differentiable continuous functions that's, you know, co-analytic complete. But as it turns out, the set of normal numbers is going to be pi 0,3 complete. Typically, things involving a limit are, let's say involving a limit existing and being equal to something tend to be here. Things where limits don't exist are more likely to be here. For example, like essentially non-normal numbers tend to live here, and normal numbers are living here. And, further understanding, what does it mean to be pi 087 complete? I have absolutely no idea what it means other than I can write the definition. I can't give any intuitive explanation of that. And there's a whole bunch of interesting things that are complete on this level, like transcendental numbers, Liouville numbers, badly approximable numbers, irrationals, and lots of stuff. So you could try, just for fun, figuring out, where, you could even try this as an exercise for tomorrow, if you want, like, where do the set of badly approximable numbers live? Where does the set of Liouville numbers live, and so on and so on. We know that the rationals and irrationals are the transcendental numbers also, algebraics. So there's a lot of still very interesting stuff already on the second level. Let me think if I have time to say too much more. It's basically right on the dot and it's ending. So just to kind of close, so tomorrow I want to give some examples of some things that are already known. I'm going to still have to be a little imprecise on one of the theorems that I want to state because it requires a lot of abstract setup. I want to state kind of a simplified hand-wavy version of this theorem and give a proof that basically generalizes the notion, or this theorem that the set of normal numbers in base B is a pi 03 complete set. So that was proven by Kyiv and Linton in '94. So we talked about on Friday all these other types of normal numbers, continued fraction normal numbers, beta normal numbers, Laurent series normal numbers, and so on and so on. So we have a theorem, I think that was already published 5 years ago, from 2020, that includes all these examples and many more. We can talk about Cantor series normal numbers and differences. I mentioned this thing in the last class about set of numbers that are continued fraction normal but not normal in any base. We can, without the generalized Riemann hypothesis, we can get a lower bound in the difference hierarchy for the complexity. We don't know an upper bound. And there's a bunch of stuff we can start attacking. I'll give like a rough sketch of how the proof techniques go. And depending on the problem, they can be kind of not too complicated at all, or they can get very hard. And this general sketch can be, I think, taken in other places than just normal numbers. And that's what I'm hoping to, if we're lucky, get some ideas and maybe other places to look. So anyways, that's it for now, and we'll, I guess, finish tomorrow. So.
Questions, please?
We say S is analytic if it is the continuous image of a Borel set. As it's like Borel map to set or to S, I mean. Or
Well, you take a Borel set, so you say start with a Polish space. And so Polish space, it's a topological space, so find a continuous function. Means the inverse image of open sets are open. And you would take the Borel set and then apply that to your continuous function and then analytic set. So that's the definition.
The notion of analyticity depends on the metric in space.
Mm-hmm. Exactly.
okay.
And it can be generalized in general topological space because continuity is.
Yeah, we didn't use anything about it being a metric space here. You could just, you can define the Borel sigma algebra on a topological space, and then we're doing all of our descriptive set theory in a Polish space, so everything works out nicely in a Polish space, but you can go more general.
Separate Hausdorff topological space.
Yeah, complete separable metrizable space.
Yes.
So, you can talk about it more generally, and maybe there's some other things that happen, but then you're probably not going to have some nice structure, the projective hierarchy and things. And I'm not going to go in that direction, but one can. If you want.
So, are you going to discuss tomorrow the dependence between topological massivity of a set and
Topological what? Say it again.
Topological massivity. I mean, first bare category, mega or co-mega set, and dependence with the classification here.
So for example, meager countable union of nowhere dense sets. I mean, I don't.
For instance, just to set that a set of
A dense G delta is co-meager.
essentially non-normal numbers out of the first Baire category is enough to show structure of the set.
Yeah. So you mean things like a dense G delta is co-meager?
Yes.
I wasn't planning on it. There's so many other things.
It's additional motivation to study descriptive set theory.
From my perspective, it's an entirely different question. So the types of questions that I'm dealing with are, that's kind of this notion of largeness, right? That, co-meagerness is a notion of largeness, and there's certain things you do with that. These have nothing to do with, largeness in the sense that co-meagerness or full measure does, or being a winning set does. So I was not planning on talking about that. I mean, if you want me to say a line or two, I guess I could, but there's so many other things that might be new that I was planning on talking about instead.
What about descriptive set theory point of view of extremely non-normal?
And which the extreme
frequency varies from 0 to 1.
It's probably sigma 03 complete.
Of course.
Yeah. So I think that's one where Dominic Kvietniak write down a proof but not publish it yet. So there's something that Dominic...
Lars Olsen published several papers on this topic.
Yeah.
And
right.
He tried and succeed to classify it in descriptive set theory of the set. So the set of 0 Hausdorff dimension, but of the second Baire category.
So I would still not call that descriptive set theory so much. That's more, I'm looking more at Borel hierarchy, which is living kind of separately than meagerness and co-meagerness. So, what I would kind of say, where is it living in the Borel hierarchy? And it's most likely sigma 03 complete. Did he prove that in his paper? He might have. There's a lot of stuff in his papers. I'm not entirely sure all of what he does, but very, very likely it's a sigma 03 complete set. And showing that a set is co-meager is very different than showing that it's complete at some level. So let me just kind of state right now then just very quickly, maybe this will help kind of clear up some of the differences here. When we're saying that a set is complete, say sigma 0 alpha or pi 0 alpha complete, what we're basically talking about is what types of theorems about the set can be true. So for example, we know that a number x is normal in base B if and only if the sequence b to the nx is uniformly distributed mod 1. If you check both of these conditions, these are both pi 03 conditions. But what if you had some reason to think, okay, a number is normal in at least one base if and only if it's irrational. So maybe okay, it's not true, but maybe one might think that, okay, if you have an irrational number, there's some sort of way to cook up a base. It's not clear what it's going to be, but to make your number normal in that base. Maybe a theorem like that could be true. But you immediately know, for example, by this Slayman and Becher characterization that that's a sigma 04 complete set, which I haven't written down, but I mentioned earlier. And then being irrational is complete on the second level, that theorem has to be false, because if those two sets, the set of irrational numbers and the set of numbers normal in at least one base, were equal, well, then they would be complete at different levels in the Borel hierarchy, therefore your theorem is not true. So it's more telling you what types of theorems can characterize sets. And if your set is not Borel, then that's a way of, in some sense, saying that there's no nice, good characterization, that things are a bit more crazy. You have to do some sort of uncountable quantifications. As opposed to co-meagerness, where this is a nice property, where it's preserved by countable intersections and whatnot. To me, it's a completely different beast. It uses language like open and closed sets and topology, but I look at it as something entirely different, but maybe that's just my perspective. Does that make sense?